podcast with Matt Scott and Joe Halsey, episode 484. Welcome to the Smart Buildings Academy podcast. All the information covered in this episode can be found on our website at podcast.smartbuildingsacademy.com/484. Today we're going to be going over HVAC calculations. Have you ever wondered why your bedroom was so cold at night, even though your furnace has been running all day? Or your basement has been humid all summer long? If you've experienced this, then you've probably experienced an undersized or oversized HVAC system. So, how do we know if it's undersized or oversized? Well, we start with something called HVAC load calculations. So, what are HVAC load calculations? An HVAC load calculation is the process of determining the cooling and heating capacity required to maintain comfortable indoor temperatures in a given space. Joe, you want to elaborate a little more on that?
Yeah, sure. I mean, a lot of people know that your house gets hot during summer and it gets cold during the wintertime a lot. But when you're doing a load calculation, what you're really doing is replacing the heat that you've lost or gained. So, heat by nature, it's going to move from a hot or a warmer temperature to a cooler temperature. So, we take, for instance, our house during the summertime. If we have it, say, around 75 degrees and it's 95 degrees outside, that heat is trying to come into our house. We call
Yeah.
that a heat gain, right?
Yeah.
And vice versa. In wintertime, we're 70 degrees in our house and it's, 20, 25, whatever outside. Well, we have a big heat difference. So we're going to be losing heat from our indoor to our outdoor. And the bigger the temperature difference, the faster that heat's going to move. So when we see those big temperature differences, that means we're moving a lot of heat faster. So when we do a load calculation, what we're really doing is we're just trying to make up for the amount of heat we're gaining during the summer and make up for the heat we're losing. So when I say we make up for heat that we're gaining during the summer, essentially we're trying to remove heat.
Yeah.
We generally measure this, and heat's measured in what's called BTUs or British thermal units. And so what we're doing is so many BTUs are coming into our house every hour. And so we
Mhm.
size our equipment based off of how many BTUs can we remove from our house every hour. So whatever our design conditions are, which we'll elaborate on momentarily, that's
Yeah.
what we're designing for. How much is coming in? We've got to get rid of it. During wintertime, how much are we losing? We've got to make up for it. So
Yep.
that's essentially the purpose of a load calculation.
Yeah, and that's a great point. And I also want to add, not only is it for a house, but also for any kind of building, whether it's a hospital or university. This expands to everything. So when we talk about these load calculations, really it applies to any kind of building that we're using or we're designing for. So why does getting this right amount of heat load or cooling load matter? And it really, if you think about going back to those examples that I gave, it matters because an undersized system or an oversized system won't heat or cool effectively, and that just, adds cost, it adds wear and tear to your system. There's so many different things that we need to take into account to make sure that our systems work properly. And you mentioned the lack of humidity control. This obviously leads to being uncomfortable, and that's such an important thing when you're designing for hospitals and even your house, right?
Yeah, exactly. And so what happens in a lot of buildings, or like you said, even in someone's home, when we're running our air conditioner, it's also serving as a dehumidifier. We have to
Mm-hmm.
remove humidity because that's a type of heat that we've got to account for. And when people don't get rid of humidity, their sweat doesn't evaporate as fast. And so they
Yeah.
don't feel cool. And so
Yep.
what do? They bump that temperature down even more,
Yeah.
right?
Yep.
But what happens then? Then you still have that kind of cool, clammy feeling because you've not really addressed what was really making you uncomfortable, which wasn't the temperature, it was more the
Yep.
humidity. So that's a big role in a heat load calculation is to address that as well as temperature.
Yeah, absolutely. And so these heat loads and these load calculations, there's multiple reasons or what the HVAC engineers are designing for. You want, as we mentioned, size and cool equipment properly. We also want to make sure that we're optimizing energy efficiency. We talked about reducing the operating costs, humidity control. What else do we have? really you're just leading to inefficient performance.
Yeah. If you think about incorrectly sized equipment, let's take a large commercial building, for instance.
Mm,
You may have a little more play in there because you may have additional dehumidification functions. So
yep.
the one of the worst things about oversizing, as we mentioned, is that you can't remove that humidity as well. The reason for that is the equipment's not running long enough, it's not going across a cold coil long enough, and it's not sweating.
Mm,
So we're not
hmm.
removing enough moisture, right? But
Yep.
then the downside is even if you have added dehumidification, what are we doing? Like you said, we
Right.
are spending money now to be
Yep.
cooling and then reheating air. We also have a larger initial cost. We have larger operating cost.
Yep.
You know, we're going to satisfy that temperature a little bit quicker. That's fine. But what does it matter if we've got to bring it all back on again just to try to get that humidity down?
Yeah, and we call that short cycling, right?
Exactly. Yeah. Yeah.
And we see that all the time. Just again, it happens, but we try to make sure that we design so where that doesn't happen and we have more efficient equipment, saves money, all those things that we just talked about. So now that we've kind of talked about our HVA load calcs and what they are and what we're designing them for, we can kind of break down the different types of HVAC loads. So we really have three different types. We have sensible, latent, and total load. Now, the sensible load is our temperature related load. So, example being the heat from the sun. That is our sensible, what we sense or what we feel, the heat. So, also from your appliances, whether it's a refrigerator or a computer. Notice sometimes when you're sitting by a bunch of monitors and it feels hotter, that's a sensible load, that you're physically feeling that load from this equipment. And so when we're doing our load calculations, we're trying to account for every piece of equipment in there, either heat from the walls or windows coming out from the outside in the sun. And we'll kind of get into weather related stuff a little more, but that's our sensible load. Then we have our latent load. Do you want to talk about the latent load a little bit?
Yeah, sure. So it kind of goes back to what we were talking about. Latent itself just means the type of heat that results in a change of state without
Hmm.
changing temperatures. But when we're talking about it in a load calculation, we're really talking about humidity. So I always put it this way: a change in sensible heat results in a change in temperature. That's
Mm.
cooling a space off or that's heating a
Yep.
space up. And then a change in latent heat, again, is just removing moisture from the air. Or in the case of heating, sometimes you may want to add moisture to the air. So you may actually want to add some latent heat to the air just to get
Yep.
those humidity levels back up some.
Yeah, exactly. No, that's a great way of thinking. And then we have our total, which is just our sensible and our load combination, right? And it's just the sum of those loads that determine our total HVAC capacity, but not necessarily does that apply to what we're designing for. So I want to make that distinction, right?
Hmm. Yeah, exactly. So a lot of people think that if they get a total load calculation, let's say it's for, I don't know, just make something up, a 20-ton unit or something, they think
Hmm.
that's what they need. But you really have to break it down, as you said, between the sensible and latent. So the
Yep.
goal of any load calculation, we try to select equipment, is we have to at least hit the sensible load that we're designing for and at least hit that latent load that we're designing for.
Exactly. Yep.
A lot of times in commercial buildings, you can't do that. Residential, you can get a piece of equipment that at design conditions can meet those. But
Yep.
with commercial, we have so many factors, which you'll get into, I'm sure, as you start
Yep.
performing that load calculation. When you have a lot of people in there, or more specifically, you're bringing in a lot of outside air, now you're bringing in a lot of humidity, and just a standard piece of equipment by itself may not be able to handle that. So that's why we have to account for that in other ways in our design process.
Yeah, exactly. That makes ton of sense, right? Now, next we kind of want to talk about those factors. And we had talked before, but really I want to go back to how an engineer comes up with the concept or the load calcs. And in most cases, we're using programs that are designed to give us these numbers. And it breaks it down from our room all the way to our chiller plants. And so in some of these programs, we can take a room and we can add a bunch of rooms and zone them, right, for our VAV boxes. Once we have all our VAV boxes, we can then add those zones to an air handling unit. once we have our air handling units, we can even tie it to a chiller plant. And so we can break it down piece by piece or system by system all the way back down to the room. And so when we're factoring in all the different things that we need for our load calculations in a room, we think of our building size and layout. So depending on where the room is facing the sun, right? We have different sun exposures or heat exposures. We look at our U values of our windows, so how big the window is from an area standpoint. I guess I need to back that up. We talk about volume in a space, so we figure out our area and also the height of the room, and we need to calculate how much volume we're satisfying, right?
Yeah, there's one other thing I would add that's really important to this. When you're doing a load calculation, if you have, say, two rooms in the middle of the building
Mhm.
and there's no exterior walls, there's really no heat difference between those rooms, with the exception of
Yeah.
whatever is in those rooms. So, as you
Yep.
said, the equipment that's in there or the people that's in there. A
Yeah,
lot of our heat
exactly.
load calculation, going back to that outside degree versus the inside degree, the temperature difference. So, when
Yep.
you think about a lot of this happens at the exterior walls, is what I'm trying to say.
Mhm.
Exterior
Yeah.
walls or
Yep.
exterior floors and ceilings or roofs, that's
Yep.
where we're losing a lot of that heat transfer. So
Yeah,
going
great
back to your
point.
point with the windows and the
Yep.
walls, basically what it boils down to, a U value just tells us how well heat can move through something. It's
Yes,
conductance
exactly.
value. It's the
Yep.
reciprocal of our R value. We all know insulation is rated at R value.
Yep.
That R is for the resistance of heat transfer. So we want to load up all of our exterior components with high R values, because
Yep.
the higher the R value, the lower the U value, the less heat is going to move in and out.
Exactly. The
So
more
yeah, when we're
insulated something is.
exactly, and so when you look at it, what we're looking at is really three factors. Now, also solar heat gain's a fourth factor when you're talking about windows, because everybody knows if you leave your windows up in the middle of summer on your vehicle, it's going to get
Yep.
hot. You get a lot of
Gonna
radiant
get
heat.
that. Yep.
Outside of that, though, basically the heat that you're losing or gaining is a matter
Mhm.
of how much surface area there is. So, how tall, how wide, what's the square footage of, say, a wall? What's
Yep.
the U value, which is how easily does heat move in and out? And then what is your delta T, or your temperature difference? The greater the
Yeah.
temperature difference, the more is going to move through that wall. So, a
Yeah,
lot of people, I
perfect.
guess, I don't want to get ahead of ourselves, but they'll use little rules of thumb, maybe just square footage of an area, right? Oh,
Yeah.
well, here we design for so many CFM or BTUs per square foot. Well, that's really leaving everything wide open. I
Yeah.
always say, what space are you talking about? Do they have 8 foot ceilings, 12 foot ceilings? Or they have all east west facing windows?
Right.
There's a lot of different dynamics and construction components that can go into that. So there really
Yeah.
is no good rule of thumb.
Yeah, and even I mean, the calculation CFM is cubic feet per minute, right? Cubic feet meaning
Right.
volume. So if you think
Exactly.
about it, that's as basic or easily of a breakdown as it gets. So when you're looking at a CFM rule, you should always be thinking of the volume. Obviously, if you have a really tall entrance to a house and this thing is 20 feet tall, it's going to be a lot more, or you're going to require a lot more air to be supplying in there to cool or heat that space as opposed to an 8-foot ceiling. And that's just, I
Exactly.
guess when
And then
you
it's
go back
even
to that CFM.
Yeah, I was gonna say it's even exacerbated on big atrium in a commercial building, a big lobby
Exactly.
area.
Yep.
Yeah, you
Yeah. And when we zone for that, we usually just zone for that space because it's so unique. Another thing about zoning, and you kind of touched on it, when you look at two rooms that are side by side and they're interior rooms, meaning there's no exterior walls, they can be zoned together in most cases because there's not much different between them, and they don't require a ton more air. There's not a lot of unique circumstances as opposed to a lobby or an atrium where you might have 3 exterior walls, you might have a big glass opening. There's just so many unique requirements to cool that space that
Oh
a lot of
yeah.
times when we're zoning for those load calcs, we specifically break out as a dedicated unit for that area.
Yeah, and as we go along, I'm particularly interested in how you go about doing that because we have slightly different backgrounds. I
Yeah.
was a mechanical contractor, and I've done a lot of residential work and training in those areas, but I was
Yep.
never a mechanical engineer. So on
Yep.
my job sites, when I would go there, this stuff had already been done. It'd been sized out for you as a mechanical
Sure.
contractor. Thank for
Yep.
someone like you, an engineer smarter than me, who has the program, would actually sit down and figure all this stuff up. Then it was just up to me to make sure it was done right. If you
Hopefully done right.
transition, hopefully, exactly. But if you transition to that to the residential side, which I did,
Yeah.
I started off in commercial. And so when I transitioned with my own company into residential, to me, it was kind of like a bit of a shell shock because all of a
Hmm.
sudden it was all on me. Like now, there was no
Yeah.
engineer designing, there was no one designing the ductwork, the load calc and everything. And so I had to learn
Yeah.
all of that science, that side of it beforehand. And I
Yeah.
did. I know we'll talk about ACCA here in a little bit. They used to have a manual in. They don't really push it so much anymore because ASHRAE kind of, they kind of regulate load calculation
They
for the
took
commercial
over
side.
everything.
You're
Yeah.
right. Yes. ACCA still pretty much handles residential, but they
Mm.
had a manual in which was commercial load calculation. And
Mm.
so I
Okay.
used to use it some,
Yeah.
smaller restaurants, maybe gas stations, those sort of smaller applications, usually just rooftop units, basically.
Sure.
But yeah, I'll be interested to hear kind of the process that you go through with your software when you're designing for a more complex commercial building.
Yeah, absolutely. So, kind of going back to what we were talking about in terms of all the different aspects of a load, and you kind of touched on it. Something that's important is the number of occupants. And so, like, the more people you have, the more heat is generated in a room. And so, one thing that was always difficult was to assume an amount of people in a room. So, like in an
Yeah,
operating
right,
room, at one time you might have 4 to 8 people, but that might only be for 1 hour of the entire day, right? And
right.
when they're doing surgery, while the rest of the day, there's nobody in there. And so it's like, do you take an average amount of people for a day? Do you take the peak load, which we talk about a little bit more? So that was always something that was challenging was figuring out what equipment is going in the room because, an MRI or something with more heat output is going to require, more cooling of a load than something like just having one computer in an office space.
Oh, right. Yeah,
And
absolutely.
so, yeah, calculating or understanding how many people are in there, understanding the workflow was something that we always had to work closely with the architects and the interior designers, and a
Yeah,
lot of
and
times
the
we're
building
waiting on.
owners for that matter.
Yeah, and
The build.
building owners,
How are they
right.
going to operate the building? Yeah,
Yeah,
yeah.
exactly, and so
Funny,
we're always,
funny
like,
story.
waiting. Oh, go ahead.
Yeah. No, yeah. I was going to tell you talking about the people load. It reminded me of a. We had like graduation, and it was in a big
Mm,
gymnasium,
yeah,
and of course those people start piling in a gymnasium, and then it
mm,
gets really really hot. We were
yep.
there as instructors, and I was there sitting beside the other HVAC instructor, and one of the other tech instructors behind us was like, "Man," he said, "how much heat you reckon all these people in here are putting off?" And, instantly I was like, "I don't know, but I bet it's a lot." Well, the other instructor,
Yeah.
he's been doing it a while, so it naturally comes to him. He just turned around, and he said 450 BTU per person. And they
Yep.
looked at me. They're like, "How come you didn't know that?" I said, "Oh, I did. I did." I said, "Oh, it's 250 sensible and 200 latent per person." I just
Yeah,
didn't
there
think
you
about
go.
it. They were like, "Yeah, yeah, okay." But no, like exactly to your point, how do you size for that? Obviously you're
Yeah,
going to have like multiple pieces of equipment or something
yep,
where most of the time, we're running
mhm,
low. But then when that thing fills up, you're going to have
yeah.
to put a lot more in there. The other place I saw it a lot would be church sanctuaries. When you're
Oh,
designing
yeah,
for a church, especially if it's a larger church, you get a
yep,
lot of people in there. But again, to your point, it's only like a few hours a week. So,
right.
how do you design
Yeah.
for those conditions efficiently, to maximize energy efficiency? So,
Yeah, exactly. Because you don't wanna oversize it as we talked about, because then you get short cycling, and so a lot of times there was a lot of redundancy, so we would
mm,
have smaller handling units that would handle a load, and then if another one needed to kick on for that peak load or when church was in session, you would have multiple units running as opposed to one big unit, and so there was a lot of times that we'd have redundancy. Also, there's an economizer that you can throw on there. There's a lot of ways to lower the amount of energy input for your system. But yeah, designing for those peak
Right.
loads is always difficult. And in most of those programs, when you input the number of people, it does ask you, or you have to understand what is the activity level of the people. So, like in a gymnasium, as we talk about, obviously, if you're running around, you're sweating more, you're putting off more heat than you are if
Right.
you're just sitting at a desk. Now, maybe if it's 100 degrees and you're nervous and something's going on,
Uh,
it might be a little
I don't
different.
know. Those of us that work for SBA, we put in some hard work at our desks, so we're
That's
generating
right.
a lot of
Yeah.
heat. But
Yeah,
we work from our
exactly.
own offices, so we can take care of ourselves.
Yeah, exactly. So, I mean, when you're looking at those programs, most of them have the activity level, and so that's a big factor
Hmm.
when looking at how many occupants or people are in those spaces.
Right.
Another
Um,
thing is that I think gets lost is lighting and how much heat lights in your room or your space can put off. And if you have a bunch of lighting in, say, a cafeteria or something, we need to factor in that amount of heat that it gives off as
right.
well.
Yeah, and I think that lighting is a really, really good point because traditionally, as you said, that was a major source of heat
Mm,
going into an area. Now that we have LEDs and different
mhm.
technologies, that
Yep.
stuff's kind of changing. So
Yeah, that's a really good point.
not only do LEDs maybe decrease your energy just from light usage, wattage usage, but also in your heat
Exactly.
load calculation.
Yeah, that's a great point, exactly. And then another factor we talk about is the climate and weather conditions, which
Mm.
ASHRAE breaks down I mean, there's so many it breaks it down into different climates. I think there's a 1 through
Hmm.
5 climate, and, I guess I could share my
Yeah.
screen. I pulled it up.
Well,
Or do you
yeah, if
have
you've
it?
got that. No, I don't have it. You can go ahead and share it. I was going to say that's an interesting point too, because I think
Yeah.
a lot of people don't realize that as an engineer, when you design, you're designing for specific conditions. Right.
Yes,
They're actual
exactly.
numbers that you're trying to hit. You're assuming we're going to keep our indoor temperature, at this temperature and at this humidity.
Yep,
And then we're assuming the outdoor condition. We have to have a design condition for that outdoors, right? And
yep,
so if
exactly.
you're looking at the ASHRAE standard, they will give you weather data for whatever city you're in or a close by
Yep,
city somewhere as close as you possibly can get. And it
yep,
will tell you the 1% and maybe the 2.5%, like heating duty hours for that year or cooling
yep,
hours. And what they're really doing is they're saying this many hours of the year, like for instance, if it's summertime, you're looking at the 1% summer, it'll
yep,
say like 94 degrees or something. What that
exactly.
means is it only gets 90 above 94 degrees 1% of the year in that climate.
Yep,
Now, that's not how many days because they're breaking it down by hours.
right.
And so by doing so, it's much more accurate.
Yeah, and that's a good point. When when we're looking at these programs, we're just putting in a zip code or a city, or we're finding the nearest city. But it is good to understand that there is an actual breakdown of climate by ASHRAE, just to understand the different zones. I'm going to share my screen here.
Yeah. And kind of something you and I had talked about while you're sharing your screen is
Yeah.
if you're designing for 1% of the year,
Yep.
right, you're able to handle that maximum heat load that you'll only see that 1% of the year. What does that mean the other
Exactly.
99% of the year,
Right.
right?
And so you can
That may bas
actually,
Yeah, I was gonna say basically it means you're oversized for
yeah, you're
99% of the year, right? You're designing
exactly.
for that 1% extreme condition.
Yeah, exactly. And so you can change the conditions of what your heat load's going to look like. So you can change the time of year you're designing towards. And so a lot of times
Hmm.
we would look at that and try to design to like 70, 80%.
Okay.
But again, the difficulty of that is what happens when it does get to that hottest day and you can't cool it and your
Hmm.
system's undersized. And so, as I kind of talked about, it really comes down to making sure you have enough redundancy and being able to hit those loads if needed. But most of the time, having a load where it's satisfying at the 70%, 80% mark.
Gotcha.
So here's
Okay.
a map, and okay, so there's 7 zones in the United States, which I guess makes sense. I mean, you have all the way down. One is so small down in Miami, all the way up to 7 in parts of Minnesota. But for the most part, you have 6 to 3
Yeah.
really in
The
most of the
down
regions.
southern Florida people, they're a different class of people anyway. They're
Yeah,
they're such a
they can
tiny group.
survive
They
that.
get yeah, they get their own classification.
Right, exactly. So
That's
so
the
they
snowbird
design.
people where we design for 80, 85 inside, to keep
That's
their blood flowing good.
Yeah, that's right. And so they take into account how dry or humid the air is, right? They take into account the temperature, and so there's different factors when they plug this in into their programs from ASHRAE. They give the wet bulb, the dry bulb. Break that down in your psychrometric chart, and they take all of that data and put it into these programs. And so it's kind of automatically engineering those load calcs for you from that standpoint.
Right. That's cool. If you don't mind, since you are the expert at doing the commercial load calculations, let's just walk through kind of like you're doing now, all the different conditions, but let's walk through
Yeah.
what that would look like from you step by step, just not in depth, but kind of, I guess you would have like
Yeah.
a program that would be fill in the blank. You would select your location
Yeah.
first, your design conditions go from there. Kind of what does
Yeah.
that look
So,
like on your end?
yeah, sure. So we would create a project, and then we would basically have that project be a building. And so we
Hmm.
create the building because we could have multiple buildings for a chiller plant, right? You could have a chiller plant serving 4 buildings
Right. Good
or
point.
an entire university system,
Hmm.
I guess a bunch of dorms or whatever it might be. So you would create your building, and then you would go through, you would look up your weather data, then you would create spaces, is what they call them.
Hmm.
And by space, really, we mean room. And we name that room, and then we'd look up the floor plan. And it does, I would say there's no right or wrong in terms of where you start. I think it's easy to start from basement or first floor and go up,
Hmm.
and really take each room by room and insert them into this program. And when we're doing that, we're taking into account, as we mentioned, the exterior walls. So I would actually have my floor plan on a piece of paper. I would take a ruler, and most times it was an eighth scale, and I would mark out how many linear feet the exterior
Hmm.
wall was. Now, if it's a corner, you have 2 sides, and I would
Right.
mark out the exterior length. And then when I would go back, and sometimes there's windows, right? And so I would mark
Hmm.
those and calculate how much linear feet of a window there would be. And then I would go into this program, and I would input my exterior walls. If it was, as you mentioned, one important thing is if it's a basement and you're on a slab, or if you're at the top of maybe a fifth floor building and you're
Hmm.
on the fifth floor, you'd have to account for the ceiling, and you could actually just put in ceiling and your square footage, and then you
Right.
could say how much of that ceiling was being covered. In most sense, it was the whole thing. And so you would basically break out the space from an exterior wall. We talked about U values of the windows or the R
Hmm.
values. You'd have to put in the insulation amount, and a lot of times we'd look at the architectural plans to get that R value, because they'll show how much insulation there is, how much
Right.
thickness of the wall, and
Hmm.
all the other aspects of your insulation. So we'd account
Right.
for that. Once we have the space, and then we start looking into, say there's a dorm room with 2 computers, and we assume 2 people are going to be living there, and maybe it's a zero point 0.5 watts per square foot power from the lighting. And so we would input all our different items, so our occupancy, our heat load from equipment, and we would do this for each room. Then we would take all those rooms and we would add them to a VAV box, and then we can kind of customize VAV box how we want.
Hmm.
And then, as I mentioned, we do that for all the systems, and then we can apply that to an air handling unit, which you can modify, as we talked about, based on what you're looking for in terms of your sensible, your
Right. Exactly.
all your latent
Hmm.
loads. and it calculates all that for you in these programs, which is awesome. I mean, it saves
Right, right.
a lot of the nitty-gritty work, but understanding how to do it, I think
Hmm.
is really
Yeah,
important.
that's pretty cool. So I guess you would say, to sum it up, you would basically, as we said, you would take all the building components and factors and all their U
Yep.
values, construction materials for every space that you have.
Yep.
You
Yep.
would come up with your heat load there and size your VAV and your airflow
Exactly.
based
Yep.
off of that. You know, your
Exactly.
cool airflow, assuming your air is going to be a certain temperature and a certain humidity to maintain the space that you need, right?
Yep.
And then you back that up, take all those, put them together to size up your air handler, and then
Exactly.
add accessories as needed. If you need reheat for additional
Perfect.
dehumidification,
Yep.
whatever, you would do
Yep.
that. You know, outside air per ASHRAE regulations for, each zone or whatever.
Exactly.
And then from there, you could take all those loads and size your chiller plant based off of that, correct?
Exactly.
So
Yep.
that's really interesting to see how that process flows.
Yeah, I mean,
Um,
it was very interesting. And I guess something we haven't really talked about, not only so I guess there's multiple ways to determine the airflow in a room.
mhm.
And one way is based on these heat loads or these load calcs from that aspect, what we explained. But another thing is the outdoor, or another thing that could dictate how much air is into a room is our outdoor air changes, right? You
Right,
want to talk
very
a little
important.
bit more
Very.
about that?
Yeah, I will. I'll back up a little bit. We
Sure.
have this in residential some as well.
Hmm.
Like we need, if you're, it's really moving there as building sciences advance and houses are much more tighter now than they used to be.
Oh
We're
yeah.
having to bring in outside air now. And so we're kind of
Sure.
having to account for that on the residential side, but it was never as big a deal. It's a
Yeah.
really big deal on the commercial side.
Oh yeah.
ASHRAE is going to require so much air changes per hour in a space because you've got a lot
Exactly.
of people there, you've got equipment, VOCs, different CO2 levels,
Yep.
indoor air quality is what we call it. So to
Yep.
handle that, generally we exhaust air out and we bring in fresh air. Well, that's all well and good, except that, you're down in Miami, like we looked at, and your fresh air is 95 degrees and like 70% humidity or something.
Ye-
So you're
Exactly.
basically pouring water into your building. And that we talked about humidity a lot, but I really need to point out ASHRAE does have standards on what you need to maintain on
Mhm.
humidity. We shoot
Yep.
for generally about 45 to 55. ASHRAE may be closer to like 40 to 60 in their range, but there's a chart you can see why it's in that range because
Mhm.
dust or viruses and bacteria, mold growth, they're all dry. Some stuff is worse in drier environments, some stuff's worse in more humid environments. So that's kind of the middle of the lane. That's that column right there where we kind of
Yep.
get the best mitigation of all those indoor air quality factors so that they're not as harmful.
Yeah, that's a great point. There's a lot that factors into that and design loads and requirements. So that's a great point. Looking and making sure, because ASHRAE dictates all of those standards and what you need to be design wise. And it's a really good point bringing up outdoor air because, yeah, if you're bringing in really hot air into a space where you're trying to get it to 70, there's going to be a lot of factors into that that you need to account for.
Mm-hmm.
But and so as I was talking about like air changes, when we were designing medical or hospital facilities, a lot of times our air changes per hour would dictate how much air would be in a room because some of these more clean-ish areas
Mm-hmm.
that we're trying to make sure that we have fresh air. So,
Mm-hmm.
for instance, our operating rooms or our surgery rooms, our pharmacy, a lot of times there's a lot of smelly things or bad things in the air, and we're trying to
Right.
quickly get that out of there and bringing in new air. And a lot of times the amount of new air that was required to be in the space would actually dictate how much air we needed to put into that so
Mm-hmm.
that we could remove the bad air. And so even if there was, two people and it was a pretty small heat load, we still needed to account for the 12 air changes per hour or 16 sometimes,
Right. Yes.
depending on the type of room.
Right, which is where you get your DOAS units, your dedicated outside air systems. A lot of
Hmm.
times, and they're really designed mostly to provide tempered air, not cold air, not for cooling
Yeah.
purposes, but as you say, just fresh air. But they
Yep.
still have to dehumidify it. So even that equipment you have to size based off of how much air is going to be coming through it, what's the conditions of the air. So they'll bring it in, they'll cool it, remove humidity, reheat it, and hopefully dump it in around 70 degrees back
Yep.
into that space because you're pulling out, like you said, tremendous amounts of air. So you're having to make up just as much, or else you're going to pull your building into a vacuum. And that's
Yeah.
especially not good if you're laid open on a surgery table and that room's in a vacuum and everybody's
Not
coughing
good.
down the hall,
Yeah,
sucking
exactly.
bacteria and viruses in there while you're laid open with no immune system. We don't we
Yep.
we try to avoid that. So.
Yeah, exactly. So breaking down those different systems are going back
Mhm.
to the programs that we use. Some of the common ones that we saw a lot were Carrier HAP and Train Trace were two popular
Mhm.
ones. Now I know there's a bunch out there, and there's some really good ones. And one thing I wanted to talk about was when we designed for we had a lot of 3D models. And so one really neat aspect, and I think as technology is evolving, we're able to implement some of this more. But we were able to take a lot of the data extracted from these 3D models. So we were working closely with the architects, the electrical engineers, the
Right.
interior designers, and they would be putting, our electrical team would have the power load in there, they would have the
Mm.
lights already in there, and so some of these 3D programs, we had Autodesk Revit, and it would calculate for you and have that data in there. And then you could extract that data and put it into Train Trace or Carrier HAP or some of
Yeah.
these
Yeah,
load
that's pretty nice,
calculations.
right?
Yeah. And then it would calculate. I mean, really,
Yeah,
what you're
instead of having
doing
to
there
chase
is,
it down and calculate it all yourself, it's already there.
yeah, it's already there. Now you had to make sure everything was inputted correctly, and you kind of have to do the checks, but it
Right.
saved a lot of time from that aspect, especially from an energy standpoint. So that was really cool to have that tool for us as well. That's
Yeah.
something that you see a lot of days with now with engineers.
Yeah, that's a really good point. And speaking of that, so I guess kind of one of the main reasons we're even talking about load calculations is for maybe building owners or contractors to
Mhm.
understand that this stuff isn't just thrown in there. There's a science behind it. And when it's
Yeah,
done
absolutely.
right and when it's operated right, you really can see good savings. You're not wasting energy, and you can
Yep.
waste a lot of energy in a
Oh,
commercial building
absolutely.
by
Yep.
just getting the sizes wrong or improper, operation for the thing. So you want to
Yeah.
kind of hit on some of the benefits, common mistakes, upsides, downsides. What
Yeah.
what what you see a lot out there?
Yeah, absolutely. And we kind of talked about this, but oversizing systems is such a big thing. And a lot of times the mistake is that, again, we design for that hot day on July 20th at 4 p.m. and every one of your AC units is 5 tons when it probably should have been 3 tons. And I've literally gone down to some of these facilities and had to change every single AC unit out because they were all oversized. And the
Wow.
humidity level was so bad, you would go into one of these classrooms, one of them was a school. You go into the classroom, you could put a piece of paper on the wall and it would just stick. And you're
Oh
like,
yeah,
clearly.
but yeah, funny story about that. We had a job at a college university, and they had a
Mm,
building that we had to put in several dehumidification systems, just straight
okay.
dehumidification, like large scale stuff. And
Yeah.
it was funny because part of their science department was in there, and what they
Mm.
would do is when they would want to grow something in a petri dish, they just swab the wall and put it in the petri
Oh
dish. They were
man.
growing all this mold and bacteria because it was just so humid and so moldy in there.
Oh
Uh,
man.
so
Wow.
yeah,
So that
that
was
that was
something
funny.
we saw a lot, of course. Another thing is when the engineers don't notice, and sometimes this is on engineers or the building owners,
Mhm.
is when you see leaks, air leaks. And if you're
Mm.
doing a renovation and the engineer has the floor plans and has the layouts, the duct layouts and the air handling units, and all they're required to do is replace some air handling units. And a mistake is either that they use that same tonnage without calculating the load that should be required,
Right.
or they miss some of the things like how old the building was and where there might be air leaks. And so
Mm,
if you're in Miami and some of that hot air is getting in, but on paper, when you're looking at the floor plan, it doesn't tell you where some of those leaks
right.
might be. And so if you don't have that intel, a lot of times that gets missed.
Right. Yeah. A lot of infiltration or exfiltration going on
Yep,
through all the, especially the older a building gets, the insulation itself,
exactly.
starts to kind of compact. And we all know the more you compact insulation, the more it loses its R value or its
Yep.
insulating ability. So, yeah,
Yeah, so
very good
that
point.
happen Yep, that happens a lot. And then also when spaces change, and or if you add a space and try to take heat or cooling and bring it into a space with not adding any more systems
Right.
to it or
Right.
adding a dedicated unit. So if you take a office room and you're like, "Hey, I want to make this into an operating room." Well, it's not designed for an operating room from a heat
Yes.
or load calculation standpoint, among other things, right? Ventilation
Right.
standards,
Right.
your
Yes.
air change hour per hour, as we mentioned.
Mm-hmm.
But it's probably not going to cool it to where you want to be and not have the humidity levels, because they have very strict humidity levels for operating rooms as well.
Right.
And
Exactly.
so that's another thing that happens a lot with
Yes.
building owners that want to change their room without, having the
Right.
right
Yeah.
standards.
Yeah. And we saw that over at the college as well. I had
I'm
the
sure.
maintenance guys, they called me over. We had this one large building that was all classrooms, right? It had a drop ceiling and your
Yeah.
thermal barrier. In other words, the insulation was on your ceiling tile, right? So what
Yep.
they wanted to do, they were changing this. It was going to be an industrial manufacturing training area
Okay.
now for those courses. So they gutted
Yeah.
it. They pulled the ceilings out, all the drop ceilings, the insulation. Now the room's like twice as tall as it was. There's no insulation
Exactly.
there.
Yeah.
They're bringing in all this equipment, and they were like, "You think this equipment's still good enough?"
You're like,
I'm like, I
no.
doubt it. No, I said, you got a
Yeah,
load
no.
calculation. I said, even though I don't have one, I can tell you, no, if it was designed for this and you've just gutted it, it's not going to work.
Yeah.
I'm sorry,
Yeah, I think a general misconception, maybe a best practice, or maybe a common mistake or a general assumption, is that if I have cooling to the room, it's going to be sufficient.
Right? Yes.
And that's almost never the case. And there's a reason why these calculations are so particular and
Mm-hmm.
why you need to account for every single thing. Yeah, there is some margin of error, absolutely, with anything. But a lot of times these spaces get changed, or there's just this assumption that if I put heat or cooling in there, and
Right.
I kind of
It's
talked
gonna
about
be
this with,
fine. Yeah.
right, with in my house, we have a sunroom that was added on after the building or after our house was built without any addition to the system. And so we're trying to extract air from the furnace and the air conditioning unit into this
Yes,
three
see that all the
season
time.
room.
Exactly.
Yeah,
Yeah, like you said, you got existing ductwork there. They're looking at,
right,
can we physically do it? Well, we've got
right.
this new sunroom. Yeah, we can
Yeah,
cut 2 duct runs off of your duct, and we can get
exactly.
air into this place with no consequences, right?
Right. And so
And
that's a
so,
common misconception that
yeah,
we
and we
see.
all know what happens there, right? So now it's probably not even enough air to condition that space anyway, number one. And two,
Yep.
you've just stole it from your house, so now your house isn't even comfortable anymore.
Yeah, exactly. And so that happens a lot. And anytime we have renovations, one thing that goes into play or comes into play is make or taking into account where our air handling unit numbers are, how much tonnage or capacity it has, and if there is some room to play, because sometimes there is room to
Mm-hmm.
play and you can bring in enough air into those spaces, but
Right.
you need to do the calculations, these load calcs, to understand if you can add more air to that space without
Yeah.
adding more units.
And just real quickly, I think we probably should we've talked about some of the problems. Let's talk about
Mhm.
how we would correct that or what some of the solutions to these are. So let's say
Yeah.
we are designing for that 1% of the year, right? Or
Mhm.
whatever, 90% of the year. And then we're oversized the rest of the year. So,
Mhm.
what are some of our design strategies to kind of overcome that? For one, I know nowadays the VRF systems are becoming
Oh,
very
yeah.
popular.
Yep.
variable refrigerant flows with inverters that can ramp up and down capacities. So some
Yep.
of these things may be able to go anywhere from 5 tons all the way up to 20 tons to match the load, needed. So it may
Yep.
only be up there at that 20 ton, a little bit of the year. And the rest of the time, it may be somewhere around, 10 to 12 tons capacity on that. What are
Yep.
some other design
Yeah.
solutions that can address that?
Yeah, as I mentioned, adjusting for the climate conditions. So maybe it's hot for that 1%, but maybe
Mm-hmm.
designing instead for the 70 to 80% and understanding that it's not going to happen other than that 1%. And so having it, there is not necessarily a sweet spot, but understanding that you shouldn't over design and that most of the time it's going to be in that 70 to 80% range. So sometimes we'll not try to go to peak load because
Mm-hmm.
most of the time these HVAC calcs are doing a max and there is margin of error in terms of
Right. Kind of a
oversizing.
built-in safety factor already
There
that
is.
that you don't want to go over to make yourself feel better because that safety's already
Yeah,
been put in there in the calculation,
exactly.
right?
Yep. And
Yeah.
another common practices, and this is more for larger buildings, but that redundancy or the daisy chaining, having
Right. Yes.
multiple air handling units serving as color multiple
Mm-hmm.
zones, but having it to where it only needs to kick on in those dire needs or those heat or
Right.
peak
Right.
loads. And so having that redundancy is more common on the commercial side.
Yes.
Now, I know on the house side, sometimes people have 2 units, right? They have the lower, especially in like Texas or hotter areas, they'll have one for their upper of their house or their second floor
Right.
and then
Yeah.
have
Generally,
one
you
on
want
the
to
first
separate
floor.
those out, because there'll always be a temperature difference there. So have
Absolutely.
a
And
unit upstairs, one for the main level.
now in
Um,
Ohio, we don't have that.
so you don't do that in Ohio, huh?
No, not very often,
That's funny.
unless your square footage of your house is probably over 5, 6,000. Most houses in
Oh, really?
Ohio, we have 1 unit. I think
Okay.
I have
Gotcha.
one three and a
Yeah.
half ton unit for my whole house.
Gotcha. Yes, yes. That makes sense. Another
Yeah.
thing I've seen a lot on the larger commercial stuff is
Mm,
in our chillers, we would have either multiple chillers or even unloading chillers
exactly.
so that they can limit their capacity just based off of
That's
what
right.
the building needs. So if you think about it, they're only going to, if they don't need to supply a whole lot of cold water, they're not
Yep.
going to, right? If you only have
Yep.
a few that need cold water and then you pair that up with variable speed blowers or
Yep.
in VFD blower motors, that those systems can kind of ramp up and down a little bit as well to try to save some of that energy. One of the
Yeah.
bad things about the traditional compressors where you're kind of staging them on and off, yeah, that's going to help some, but I do think the inverter
Mm,
compressors
mhm.
are a lot more efficient because
And
instead
more
of
common
being
now.
right, exactly, they're just an easier solution for the most part. Until they tear up, then they're not. But but
Yeah.
yeah, being able to ramp that capacity up and down, I think is kind of important nowadays. That's kind of where we're leaning towards, in my opinion.
Yeah, no, I definitely would agree with that, and to touch on the chiller plants, yeah, I don't know if on the commercial side, if you, almost ever see 1 chiller nowadays
Right.
because of that. I mean, a lot of times it'll have the one chiller A will have a 75% usage and you'll be using the chiller B at 25%.
Mm-hmm.
And a lot of that is for efficiency usage, making sure that you're not overusing one chiller a lot of times as well. There's a lot
Right.
of
Right.
design into those as well, but a big factor is load counts and yeah,
Mm-hmm.
not oversizing and being efficient for your building.
Right.
Um, so let's wrap this up.
Mm-hmm.
Let's see. I'll cut some of that. Let's see. Okay. So let's kind of wrap this up by going over why it's important to properly size equipment.
Sure.
One of the things is definitely comfort for your occupants. I don't know if there's anything more important. I know money is very important,
Right.
but if
And
you have
health and
in health,
safety.
yes, right, health and safety are definitely important. But if you don't have happy people in your buildings, you probably won't have a
Yeah.
building for very long.
Yeah. That was the first thing I was ever taught in
Mhm.
HVAC was that you're not selling equipment, you're selling comfort. Always
That's right.
remember that. You're selling comfort. So, but
Yeah,
again,
I
in
think
commercial buildings, you do have the health issues again with the mold and everything, the indoor air quality.
for
That's
sure.
part of it as well. But yeah, definitely got to keep the customer happy.
Yeah, absolutely. And then we kind of branch down to, longer equipment lifespan, making sure
Mm,
that this equipment doesn't break down a lot, that you get the most out of your equipment, and that comes down to, more energy efficiency and cost savings from a long-term standpoint.
right.
Those are clearly very important.
Yes.
Some other things to kind of remember are having those cooling, the latent and the sensible loads.
Hmm.
Understanding those is very important. Also using the industry standards, ASHRAE. If you want to look up more, just read any ASHRAE book. There's 90.1. There's a lot of different books that ASHRAE will break down load calcs and more, of course.
Right. Right. Yes, I agree. And it's also important to remember that we are aiming generally for specific targets, as we had
Mm,
said. We're designing, it is very quantitative based off a number.
yeah.
An engineer can't design something without having accurate numbers to go by. So,
Yep.
if you're listening to this and you're, architect or someone else, it's really important to get them the information that they need because that's what they're designing for.
Yep.
If we say it's going to be one way and that's what it's designed for, and then it ends up changing and being something else completely different, that can be a problem. And a lot of building owners don't realize that during the design phase, how much a simple change can affect even something like the HVAC equipment.
Yeah, those are all good points. I think this kind of wraps it up, but did you want to touch on anything else?
No, I think we pretty well covered it, just keeping those basics in mind, why we do it, what to expect from it.
Yeah, awesome. Well, thank you for listening to the Smart Buildings Academy podcast. We hope you learned from this episode. If you found this episode valuable, please leave us a 5-star review on Apple Podcasts or Spotify. If you're watching this on YouTube, please like, comment, and subscribe. And if you're watching this on LinkedIn, please share this with your network. As always, this will be available on our website at podcast.smartbuildingsacademy.com/.